All right, I did look through the prelim topic review survey I posted. Only about 30 people replied, and the answers for what to cover were basically everything. There was no overwhelming tilt towards one specific topic, so what I am going to attempt to do today is kind of do a recap, a high-level recap of everything, where I'm not going to have time to write down every single equation, but kind of give you an idea of how, if I was a student and I was going to take this exam, how would I structure my equation sheet? And that's not necessarily a hint or saying how you should do it. That might be more how I think, and people might have different styles or something, but kind of maybe reminding you of some things we did at the beginning of the semester, and then depending on how much time is left, maybe getting into more detail on specific topics, but I can't repeat the last 20 lectures in full in the next 50 minutes. So going way back to day one, right? The stuff we started with at the beginning, and the stuff, some of which you should remember from physics. I think one way you can think about the material we've seen in this course, and this was one of the requests in that spreadsheet, was kind of looking at it at a component level, right? Like, what are all the individual parts we have learned? So you have, hand up in front of me now, resistors, capacitors, inductors, we learned op amps, we learned diodes, okay, we learned BJTs, we learned MOSFETs. I drew that a little too small. Okay, in addition to that, we learned batteries or voltage sources, which could be represented either by that battery symbol or by kind of a circle symbol. We did current sources. We also had measurement devices, right? So you can have a voltmeter, not to be mixed up with the voltage source. That's why I kind of prefer this symbol for a battery, so you don't get the voltmeter as a measurement device mixed up with the voltage source symbol. You can have an ammeter. I am trying to do this from memory, so I think, okay, there's switches, right? We learned both switches and push buttons. Am I forgetting anything? Pop quiz. Again, I did that from memory.
Potentiometer.
Potentiometer, okay, so that's kind of a variation on the resistor, right, where we have this 3-terminal device with the arrow representing the middle connection on the potentiometer. LEDs, which are kind of a variation on the diode with the little arrows sticking out. Mathematically, the behavior is the same, but they also emit light. Other stuff we're forgetting?
Current source?
Current source is right there.
Oh, I missed that, sorry.
Okay. Okay, so it's probably, and each one of these things, and this is what I'm not going to have time to do, or I would just be standing here writing for the next 30 minutes, right? Each one of for almost all of these things, there's at least one equation or graph or something associated with it, right? So just kind of breaking out, I'm just going to use resistors as an example, and then I would suggest you go through and fill this in for all of these other parts, right? So for resistors, we know we have Ohm's law of V equals IR, and then you have the rule that resistances add in series, so Req equals R1 plus R2, and then resistances add inversely in parallel, so 1 over Req equals 1 over R1 plus 1 over R2, and then that continues if you keep adding more in series and parallel. Right, so if you were going to put, I've really spread this out here, but if you were going to put all this in a table, right, you could have a row for each component, and then the equation, and maybe any additional rules. Okay, kind of, I'm gonna spot pick a couple other examples here. Again, I'm not going to go through all of them. Say, for the resistor, you probably don't really need a graph, but for a diode, kind of the understanding of that graph of IV behavior is important, right, where you have that IV graph, and the current is 0 until you hit that forward voltage or threshold voltage, and then the voltage drop across the diode is fixed, right? So we don't really have an equation for the diode, but we have that graph with the two regions describing the behavior. Okay, for all of the source and measurement stuff, remember we had both ideal and practical or realistic examples. So for the, I'm just picking on the battery as an example, right? A practical or real battery has some non-zero source resistance in series with the battery. Okay, so again, I'm not going to stand here and do all of these things, but this is kind of one way you could think about organizing the information, right? You have the individual part level, and then each part is going to have kind of an equation or a graph or set of equations or rules associated with. For capacitors and inductors, and I think at one point I did do a table with this just for resistors, capacitors, and inductors, right? There are continuity and steady state rules for those. Okay. For the button and switch, we don't really have an equation, but you should know, okay, when it's closed, it just acts like a short circuit. There's no voltage drop across it. There's no resistance to it. Okay. This is, see, people are still jotting this down, but it looks like everyone is here. I'm going to activate the first poll everywhere because this was something I got on the mid-semester feedback. So this document cam only has kind of 2 discrete zoom levels. I've been staying here so you can see the whole page. I can zoom in so it's bigger, but then I would have to kind of scroll around. So my handwriting sucks, that's not going to change, but I can zoom in more. A couple people asked about that on the mid-semester feedback, so we're just going to put it to a vote. Should I zoom in, yes or no? So if you answer yes, that means you want it zoomed in 1 level. If you answer no, it means you want it like this so you can see the whole page.
Is there a way to make the lighting potentially better? I think it's more the lighting.
More of a lighting issue. The problem with that is I can do, let's see, so that turned the aisle lights off. There's this dinky little light on the document cam, but I cannot get more light directly on the document camera without turning on these lights, which then wash out the board. So, yeah, I wish the built-in light on the document camera was brighter. I mean, I can make the room lights darker, like I can turn, did that help at all? I figured like if those are off, then it's harder for people to see your own writing. So, I don't know, is that better or worse? What do you say? Okay, well I guess, okay, wait, so, okay. So we're gonna do it, so answer this one, or we'll figure out the zoom first, and then I don't have a poll everywhere for it, but we'll just do the lighting. Okay, so I'm going to close, give it 10 seconds for this. Should I zoom in farther on the document cam? 5, 4, 3, 2, 1. Deactivate. Okay. Answers are in. 74% said no, I should not zoom in. So if you're in the 26% that do think I should zoom in, I apologize, but we're going to go with majority rule here. Next question then, I don't have a poll everywhere for this, so I guess raise your hand if you like it better with those lights off. Not the half-ass elbow thing, like raise your hand up so I can actually see it. Come on, okay. Hands down. Raise your hands better if you like it with these lights on. Okay, that's like almost an even split. Maybe I didn't count, but maybe a little higher for lights on. Okay, so it looks like we're majority vote for keeping it like this. Again, if you lost out on that vote, I apologize, but there's no way for me to keep everybody happy. I guess the only other thing I can do, I can like move this arm down a little bit so it's maybe a little bigger, but we can still see almost the entire page. Okay. Although that does remind me, if you ever like totally can't see or need me to clarify something, don't be shy. Like I'm not going to bite. You can raise your hand in lecture and say like, hey, I can't see that, or that was particularly messy, could you please rewrite that less terribly or something? And I can always do that. Okay. And again, depending on how much time we left, I can certainly circle back. I know talking about lighting and zoom levels is very exciting, but let's keep it down. I can certainly circle back and talk about, guys, don't make me do the thing with it. So My daughter's elementary school, they call it Quiet Coyote. Did you guys grow up with this in elementary school, or is that a newer thing where everybody has to raise your hand and make a little coyote symbol with your hand until everyone in the room is quiet? My wife has literally had to do this at the vet school. So I don't want to have to do it here, but if my 3rd grade daughter can do it, you guys can do it. Okay. All right. Kind of quick or high level questions about this stuff, again, without like really diving into the weeds on like a capacitor example or something, before we kind of switch on to other things we could think about or stuff you should have on the equation sheet. Okay? So again, that's kind of the high level, say parts table. You're going to have a table of all the different parts, what the circuit diagram symbol is, what the I didn't mention for the, say for example, the BJT or something. Some of these things have names for the pins, right? A resistor doesn't really have the names for the 2 pins. For the LED, you have the cathode and the anode. For the transistors, you have different names for the pins. For the op amp, there's the inputs and the outputs. So again, some parts are going to have a name for the pins, some aren't, but make sure you know that too. Okay? So another way to think about this, or kind of some stuff you should have on the equation sheet, is the fundamental physical laws that apply to everything, right? So it's important to remember Ohm's law only applies to resistors, okay? Don't try to apply Ohm's law to a capacitor. But we have Kirchhoff's current law and Kirchhoff's voltage law. Those always apply to everything, regardless of which one of these parts it is, okay? Currents are always the same in series. Voltages always add in series and are the same in parallel, right? So KCL, regardless of what this thing is, so just thing 1 and thing 2, right? If those things are in series, then the current I1 has to equal the current I2. Again, I don't care what these things are. Okay? If I have a node or a junction, right, with 3 things, 1, 2, and 3, then I know the currents flowing into and out of that node. If I define currents into the node as positive and currents out of the node as negative, those have to sum to 0. I mean, this is where the water analogy comes in handy. Just think of it like conservation of mass if those were pipes and it was water, right? That point is not a source or a sink. I can't have water or electrons either being generated from it or disappearing into it. So they have to go somewhere in one of the pipes or wires, right? So if, and this is where the sign convention thing comes in, if I define, say, positive current, because these are all passive elements, flowing from the positive to negative terminal of each element, then the way I've defined those currents, if I look at this node and say, okay, positive currents are coming into the node, and that's going to equal the sum of the 2 currents leaving the node, right? So the way I've drawn the arrows there, it's pretty obvious. I1 equals I2 plus I3. Technically, the language of how Kirchhoff's current law is written is the sum of all currents entering a node must equal 0. So that means if I sum the currents, well, these 2 are negative, so that would be I1 minus I2 minus I3 equals 0, right? Clearly, that's the same equation, just with the currents brought over to this side. I think that first form is more intuitive, but this is the same thing. If I do this, say I solve this circuit, I have this circuit and I2 is an unknown, and I solve for I2 and I get a negative number, then that means, okay, I2 was actually flowing the other direction from the way I had the sign convention defined, but then I'm still okay with conservation of charge or conservation of mass, right? Because if I1 and I2 are both flowing in, I3 can then still be flowing out, right? It would be impossible for me to get negative numbers for both I2 and I3, because then that would mean all 3 of my currents are flowing into the node, which is physically impossible. Okay, so again, water analogy kind of helps there. Just think of it like conservation of mass. Okay, and then we have KVL, right, where if we have things in series, again, don't care what those things are. Okay, in that case, say I have voltage V1 and V2, the total voltage drop across those two elements is going to be V1 plus V2. Okay, because they're in series. If I have things in parallel, which usually we've drawn like this, then their V1 is going to be equal V2. Remember that from the very beginning of the semester, electrically in parallel is not the same thing as geometrically in parallel. This was on that concept test way back at the beginning of the semester. If I have a thing here, and the second thing branches off like that, so it is geometrically perpendicular in the circuit diagram, that is still electrically in parallel. Remember, because these are both just connected at their two terminals. Okay, so the orientation in which I draw this thing is arbitrary, right? I could put it here, I could put it here. It's still connected by in the circuit diagram, just these ideal zero resistance wires. Okay, so I can draw that at any angle I want. Usually, the textbook convention, just to make life easier, is to put things in series like this and in parallel like that, but it's not always like that. Okay, things can be rotated by 90 degrees or 45 degrees or whatever. Okay, and again, these two laws apply to everything on this page. Okay, unlike Ohm's law or the capacitor equation or your ideal op-amp assumptions or the diode graph that are only going to apply to each individual component, these always apply to everything. Okay, so questions on KCL and KVL? No? Okay, I see people still writing, so I'll give it a second there.
Quick question.
Yes?
What was the comment that you said for that last schematic, that they're equal, or what was the...
So, the comment for this one here, that the geometric or physical orientation of where I put thing 2 on this page does not change the fact that they are electrically in parallel as long as I don't change how these wires are connected. Okay, so don't like, this diagram is electrically equivalent to this diagram. Part 2 has just been rotated 90 degrees, which as circuit diagrams get more complex and you need to mash or rearrange things in there, does not change that if you trace the, well, lots of handwriting, those should be connected there. That if you trace the wires, those two parts are still connected at those two nodes.
Thank you.
Okay? All right, let me check. All right. We are going to switch to a new piece of paper. Another way to think about this, and stuff I would recommend having on the equation sheet, is this is the individual component level, right? But we've also done a lot of what happens when you combine these things. Okay, so circuits that do stuff with multiple of these components in one circuit. So I'm going to start out with cough, cough, hint, hint, a voltage divider. Okay, something we have seen a lot of. Okay, so this is, now I just talked about circuits that are using multiple different components. This one happens to just use 2 resistors, right? But we've seen what happens when you combine a resistor and a capacitor, or a resistor and a diode, or an op-amp and a couple resistors, right? So if we look at a voltage divider as an example, this is a circuit that has, for most of these circuits, we've talked about them in terms of an input and an output, right? There's some input voltage or signal to the circuit. The circuit does something to that voltage, and there is some output voltage from the circuit that depends on what the parts in the circuit are, right? So in this case, I have an equation. V out equals R2 over R1 plus R2 times Vn, right? And there's kind of 2 different ways a problem, we've seen both of these, 2 different ways a problem could ask you to do something with a circuit like this. One is kind of the analysis approach, where you are given the circuit, right? I can hand you a voltage divider and say, okay, R1 is 100 ohms, R2 is 300 ohms, Vn is 4 volts, what is V out, right? That's just kind of the straightforward plug and chug approach. The other approach that I think is more interesting and more useful in the future, right? Like when you get a job, people aren't just going to hand you a circuit to say solve for V out, right? You are going to need a circuit to do something, and you're going to need to figure out from your library of circuits, okay, which circuit do I use to do that? So there's also the design approach, where you're not doing this forward and being handed the circuit and saying solve for V out. You're being given a problem and saying, hey, I need to divide a voltage in half, right? Or I need to divide a voltage by 1/3. How do I do it? And then you have to have, and again, it might be kind of useful to have this information in a table where, okay, one row of that table is voltage divider, and to pick another example, let's say the next row of that table is high pass filter. Not necessarily, I kind of skipped over low pass filter there, but just to kind of jump around the table, right? So your next example would be, here's a high pass filter. We have a capacitor and a resistor, V in and V out, and there is some equation, which I don't have memorized, for the magnitude of V out over V in is some function of R and C and omega, where omega is the angular frequency, because now we're driving this with a sine wave, right? So again, you could be asked to approach this from an analysis perspective, where you're given a high pass filter, or you're given this circuit and say, hey, this, I send a 100 hertz signal into this. What is the magnitude of the output signal, right? Or you could be asked to analyze that from a design perspective. Like, hey, I have these different frequencies and I need to filter out this frequency. Design a circuit that'll do that. Okay, so if you have a table, I think, I didn't write out the sentences here, but it might help to kind of write down a description or a sentence in words that make sense to you for what each circuit does. Okay, so divide a voltage, filter out. We're actually going to launch this one as a pull editor again. What does a high pass filter do? Now, if you forget the math, if you just have to describe it in words, high pass filter, what does it do? Okay, this one should be pretty quick. 10 seconds. 5, 4, 3, 2, 1. Deactivate. Responses. Okay, 98% correct. A, filters out low frequencies and lets high frequencies through. Okay, high pass. It is passing the high frequencies. So this is another one where, again, for many of the individual components, I drew the diode graph, right? For a high pass filter, we had a frequency response graph, okay, where the shape of the graph kind of looked like this, right? We are attenuating or removing those low frequency signals and letting high frequency signals through. Okay, so however this makes sense to you, right? We have this whole library of circuits. Okay, we had voltage dividers, low and high pass filters, half a dozen different op-amp circuits. I'm not going to take all the time to draw those today. Okay, a couple interesting circuits with diodes, then going on to transistors. So rather than, again, I would still have all of this information, okay, the information for all of the individual parts, but you're probably not going to be asked to analyze just a lone resistor on its own, right? Those parts are the building blocks. Okay, and then the circuits that actually accomplish tasks use multiple parts. So if you have a, name of the circuit, circuit diagram, relevant equations, relevant graph, written description for this circuit filters out low frequencies and lets high frequencies through. Or, for op-amps, this circuit, a non-inverting amplifier amplifies a voltage without turning the sign, right? That would allow you on the exam, if you're given a problem to ask you to do something, kind of quickly just go look up, oh, this is the circuit I need to do that thing, rather than just having a bunch of diagrams written down, oh crap, which one of these does that? Okay. Questions? And again, it looks like we'll have some time left, so maybe I can get into more specific examples when I'm kind of trying to do a really high-level overview here first. Yes, way in the back.
What's the difference between an active high-pass filter and a non-active high-pass filter?
Active high-pass filter, so the question is, what is the difference between an active high-pass filter and a non-active high-pass filter? This is a regular high-pass filter only made from passive components, so a capacitor and a resistor. An active high-pass filter has an op-amp in it and can amplify the magnitude of the output. So for this passive high-pass filter, that magnitude can never be greater than 1. The output, at most, that, as in this case, as the frequency approaches infinity, this ratio will approach 1, but it can never be greater than 1. For the circuit with an op-amp, you can amplify it so that output ratio could be 2 or 10 or 100 or anything, depending on the value of the resistors you pick. Same for active low pass. Yes?
Yeah, can you go over the formulas for cutoff frequency for high pass filter, low pass filter?
If I can find them in my notes, yes. Question is, can I go over the formula for cutoff frequencies for high and low pass filter? Because I don't have that one memorized and I don't want to mess up writing it down. So give me 1 second. I'm 99% sure. Here we go. 1 over RC. So in Hertz, should be the inverse of the time constant, 1 over RC. So that gives you where, let me see if I have this. The output is about 70.7% of the input without worrying about decibels. I forget if I talked about decibels, but a lot of time, when you, especially in audio or electrical power applications, we do the y-axis of this graph is scaled differently in decibels, but we're not worried about in this class. So in either a high pass or low pass, that cutoff frequency is basically where the output is attenuated by about 30%, and you have 70% of the input left. Okay? Yes?
And is that frequency in radians per second or in hertz?
F is in hertz, omega is in radians per second. So be careful which variable you see. Yes?
So if we're basically labeling that frequency on that.
Sorry, can you talk a little louder?
Yeah. If we're labeling that frequency on that graph, like we would need it wouldn't be 1 over RC, but it'd be 2 pi.
That's what, sorry, did I mess up and miss a, oh sorry, so this graph, I had written omega here, right? So it's, omega is 2 pi f, right? Did I screw that up? Omega equals 2 pi f. Okay, so if you need to convert between those two, then there will be a 2 pi in there somewhere, depending on which one you're using on the graph. So either omega or f there. But the shape of that graph, the important part of the behavior, that it's high or low pass, doesn't change if you're just scaling the x-axis by a factor of 2 pi, right? It's still going to be low pass or high pass. Okay?
Do we need to know any Arduino stuff?
Do you need to know any Arduino stuff? Is that the question?
Yeah.
Do you need to know Arduino stuff? Yes. Do you need information from the datasheet or about from the pinout diagram or datasheet on your equation? No. If you need that on the exam, that will be provided for you. If you want to write your own additional notes or like little snippets of example code or something about the different registers, you certainly can, but since the pinout diagram is so huge and the datasheet is like 400 pages long, I'm not expecting you to try and condense any of that information on your datasheet. So I would focus, in terms of making the datasheet, more on just making your equation sheet more on what we've been talking about so far. I'll also think about proportionally where the exam is in the semester, right? So far we have spent most of our time on the circuit stuff, and the Arduino stuff is just new in the last couple weeks, so I'm not going to give an exam that's 90% Arduino, right? Because that would be disproportionate to what we've covered so far. But yes, you should know basically everything up through homework 6 is included, can be included as fair game for the exam. Okay? Let me grab another piece of paper. Another thing that I think is important and probably the biggest ongoing misconception or we are going to run this. It has a pole everywhere. I have a 12-volt battery, a 10 kilo ohm resistor, an open switch, maybe you can see where this is going, and a 10 kilo ohm resistor. And I've defined ground or 0 volts as there. What is the voltage at point A? Activates. 0 volts, 6 volts, or 12 volts? Yes. Let me think. So the question was, do we have to write out code on the exam? I'm not going to answer that and give away exactly what is on the exam, but since it is a paper-based exam and you cannot run a program to see if it works. Okay, so I would not necessarily make you write an entire program since there's no way to kind of run it and verify that it's correct, but you could be asked to kind of write individual lines or snippets of code. Okay. So you should be comfortable with the registers we've used so far and what those registers do. Okay, but I am not a fan of entirely coding paper-based exams. Okay. Okay. I'm going to leave this one up for another 10 seconds. Okay. 5, 4, 3, 2, 1. Deactivates. Let's check. Okay, 75% of you answered correctly. C, 12 volts. Okay, so that is certainly higher than when we first did this question at the beginning of the semester, and I think more than half of the class got this wrong. If you answered A or B, this is a really important misconception that you need to clear up. Okay, so write down, like in all caps in bold, the voltage drop across a resistor with 0 current is 0. Okay, so look at this circuit. I have ground defined there. Ground is where I define 0 volts. Okay. I have a 12-volt battery. I know my voltage there must be 12 volts. I have an open switch, so I know the current in this circuit must be 0. I equals 0. If the current through this resistor is 0, the voltage drop across that resistor is 0. Okay, so the voltage drop across that resistor is 0. That means I have to have 12 volts on both sides. Okay, this is a, I think, misconception or misapplication of Ohm's law, where maybe you see V equals IR, and oh, if I is 0, then the voltage must also be 0. That doesn't mean the voltage at that point relative to ground. Okay, Ohm's law gives you the voltage drop across a resistor. Super important. We have seen this 4 different times, I think, throughout the semester, right? Where we also have the step response of an RC circuit in steady state, right? Where eventually the capacitor is in steady state, so the current becomes 0. Okay, current is 0 there. So we talked about a capacitor acts like an open circuit in steady state, which is the same as an open switch. So we saw the same thing there. We saw at one point the voltage clipper circuit with a diode, where if that V-in voltage was not high enough for the diode to be forward conducting, then there was no current through the diode. Okay, so then the voltage drop across that resistor was 0 and V out was equal to V in. Okay, so 3 different circuits that all kind of behave exactly the same way, right? Where there's certain special condition where these parts aren't literally switches, but they will act like an open switch with no current. And in all 3 cases, the voltage drop across the resistor, the voltage change from there to there is 0. Okay, again, not always true in these, because I could have a changing input voltage, so I have some current, or I have an input voltage that is high enough that the diode is conducting, and then I do have current through the resistors. So both of those, again, it's not always 0, okay, but conceptually can be similar to here in certain circumstances. Yes?
If that 10 kilo ohm resistor was a diode, what would the voltage be at A?
If the 10 kilo ohm resistor was a diode, then, let me think. So if we had a diode there, so that doesn't change, that we still have 0 volts there, 12 volts there. The diode is not forward conducting, so I think it would be undefined or floating in that point, because you don't have, or would it also be 12 volts? Give me a second.
It'd be 12 volts minus the...
Well, no, the diode can't be conducting, so you cannot have a drop over the diode. So our diode IV graph looks like that. Okay, where the diode's not conducting, so anywhere we have 0 current, technically according to this graph with 0 current, you can have any voltage drop across a diode. But I think that that's basically like asking if you, I think in that case it is actually undefined. It's not 12 volts like you have with the resistor. Because the resistor, in this case, you can kind of think of the resistor just like adding a length of wire to the end of a battery terminal, right? The wire has some resistance to it, so the longer that wire gets, you'll still be able to hook up a multimeter and measure voltage across it, but it is always just going to be equal to the open circuit voltage of the battery. I would have to check this with a multimeter to see what would actually measure if you do that. I think it's either going to be, well, that gets tricky because with a real multimeter, technically it's going to allow some small amount of current to flow, so the diode's going to conduct, and then you might actually measure 11.3 there, or whatever. In the ideal case where you have an ideal diode and an ideal multimeter, I'm not actually sure. Okay. Was there another hand up front, or was that just a hair scratch? Okay. The one more case I was going to talk about here that's a little different, but we saw this with op amps too, right? Where you may have, say, a resistor connected to an input terminal of an op amp, and remember our ideal op amp assumption is that the input terminals of the op amp draw no current. So if I have, say, some input voltage V in there, so then I assume the current through that resistor is 0, so the input voltage V subscript plus on the input terminal of the op amp is just equal to whatever that voltage is, because there's no voltage drop over this resistor. Okay, so that is not necessarily an exhaustive list. Those are the 4 examples I can think of right now. Okay, switch, capacitor in steady state, diode when not forward biased, op amp. This may have come up other times throughout the semester, but again, don't get tricked by this, oh, Ohm's law, everything is 0, therefore the voltage there is 0. Don't get, and then maybe this is a good time to talk about voltage more generally, right? If we just have a circuit with 3 resistors in series, there is and say I have points, I don't know, A, B, C, and D. If I just ask, what is the voltage at a point? That means referenced relative to ground, which is 0 volts, right? So if I ask, what is the voltage at node B in this circuit? That means the voltage here relative to ground, which is the voltage drop over both of these resistors, okay? And if I call those resistors R1, R2, and R3, that is not the same as asking what is the voltage drop over resistor R2. Okay, the voltage drop over resistor R2 is the voltage at B minus the voltage at C. Okay, so always remember that voltage is referenced or measured between 2 points. Sometimes it is implied that the second point is ground. That is not, actually, sorry, that is the case here when I ask what is the voltage at A. Okay, I mean what is relative to ground, but the voltage at A is not the same thing as the voltage drop over that resistor. Okay, the other mistaken answer there, those of you who said 6 volts, you kind of had the right idea if you started out and looked at that and thought it's a voltage divider, right? Because we have 2 equal resistors, so it's going to divide the voltage in half, only when the switch is closed. If the switch is closed, that would be true, but when the switch is open, that is not behaving like a voltage divider. Okay? Yes?
So in the op-amp,
Yes?
it says VT, like what is?
Sorry, V subscript plus, so the voltage at the non-inverting input,
Which will be VN.
which is, yes, equal to Vn because there's no current through this resistor. Okay? All right. Let me, I guess, really briefly talk about Arduino stuff since we have a few minutes left. Okay? So most of what we've seen so far with Arduino has been controlling LEDs, where we have this little flag symbol to represent, say, an Arduino pin, and then we have an LED with a current limiting resistor, and then we can have a button connected in different configurations. Okay, so we saw a button like this with a pull down resistor. Okay, and then, so when I push this button, the voltage goes high. When the button is released, the voltage is low. And then again, information about registers will be provided on the exam, but if you want to jot down some of the key ones on your equation sheet in language that makes sense to you too, that's okay. So that's set. We have the DDR register that sets the input or output status of the pin. We have the port register, sets an output on or off, or high or low. And then the pin register, which reads the states of the pins. And then we had a bunch of, I'm not going to write down all the interrupt registers now, but then we also had, so we used polling, where we just use an if statement to check if the button pushes high, turn the LED on, and then different interrupts that could kind of instantly detect if the button was pushed instead of having to wait to get back to the top of the while loop. Thinking, I also kind of never formally wrote this down, but probably should have. If you want to have a little table, so high, true, 5 volts, or 1, all kind of mean the same thing when we're talking about digital logic. Same with low, false, 0 volts, or just a binary 0, right? I kind of may have used all these terms kind of interchangeably in lecture, right? When I say set the pin high, or you could add on or off to this table. Okay, set the pin high, turn the pin on, set the bit to 1. Don't get the numbers mixed up. The Arduino is operating at 5 volt logic. So when a pin is set, when you set a bit to 1, that doesn't mean the output voltage is 1. The output voltage is 5 volts. Same thing when you push a button and read a voltage. So the physical voltage, if you hooked up a multimeter on the button, would be 5 volts, not 1 volt. But the code is using 1s and 0s in the registers. We talked about masking, which again, I'm not going to write down the whole table for that here, but using bitwise operators to if you just want to turn one bit in a register on or off without affecting the other bits. So again, pretty much everything that's in homework 6. Questions on, we got 5 minutes left. So either quick questions on the Arduino stuff or like going back to any of the more specific stuff about the other things so far. Yes?
Can you go over inductors really quick?
Sorry, can I go over inductors really quick? Sure. So, inductor, physically it is literally a coil of wire that stores energy in a magnetic field. Okay, give me 1 second to find my inductor notes so I don't mess up the equation. Actually, I am, okay, I can't find my inductor notes, but I am 99% sure the equation is V equals L di dt, where L is the inductance in henries. Okay, so, and I think the main thing we talked about with inductors and the need for a flyback diode is the problem with that is if you have a circuit with a closed switch in series with an inductor and the switch opens suddenly, right, well when the switch opens, if we were to make a graph of current versus time, and we had just the switch was closed, there was some current flowing through the inductor, and we open the switch, so the current wants to drop to 0. So that means that this derivative approaches negative infinity, right? I have a very large negative derivative of the current, which induces a very large negative voltage across the inductor, so a reverse voltage, where previously I had current flowing the other way and voltage across the inductor would have been equal to the voltage across the battery, and now it induces this really large reverse voltage spike, which when this switch is open can cause a spark across the gap and damage the switch. So then we talked about adding a flyback diode like this. So normally when the switch is closed, the diode is reverse biased, so no current can flow through the diode, the current goes to the inductor, but then when the switch opens, that kind of gives that current generated by the reverse voltage a safe path to discharge across the diode. And again, there are separate continuity rules for the inductor as opposed to the capacitor. In steady state, an inductor acts like a short circuit as opposed to a capacitor acting like an open circuit, so there's no voltage drop across it. And for continuity, again, the current, sorry, I want to make sure I say this right. The current through an inductor has to be, in the physical world, right, like when we open a switch, that's kind of creating this discontinuity, but mathematically the current across an inductor has to be continuous to avoid infinite voltage. Okay? Again, that's a, I think if you, there should be a whole video in the circuit theory playlist if you want to watch the whole like 10 or 12 minute walkthrough of inductors or whatever it is, but that's the 2-minute version. Okay, yes?
Yeah, sorry. So in the original note for the inductor, I think on, like from the positive terminal as you've drawn it, from the inductor to the diode, there was a resistor, so I want to make sure that's...
So I drew that, technically this circuit, since an inductor acts like a short circuit in steady state, if you just hook it up to a battery like that, then in steady state that's like shorting the battery. I drew the resistor just to indicate that the inductor, in reality, a physical inductor is also going to have some resistance to it because it's a very long coil of wire. But what I said here about the flyback diode and the concept of giving the current a safe path to go doesn't change if we put the resistor in there or not. Hold on. Let me check. All right, hey, all right, never mind. Now it's 12:05. Okay, now you can go. All right, I will stick around for questions afterwards and make sure you get that answered. All right.
Quick